In this video, I want to introduce you to the concept of the mole. We're going to come to a few different ways of viewing what a mole is, or a few different definitions for the mole. But to start with, the first definition that I'd like to use is to think of the mole as a set number of atoms or molecules or particles. One mole is 602 times 10 to the 23 atoms. So it's an enormous number of atoms. It's incredibly large. Basically, you can go online and see all kinds of interesting things, like if you had a mole of pennies, they would stack this high, or those sorts of things. And you'll find all kinds of interesting stuff doing that. But it's basically a number that's so large that it's unimaginable. To simplify it, we can compare it to something that we're a little bit more used to that is simple. A set number of things that we're used to using is the dozen. We might say 1 dozen donuts or 1 dozen eggs, and what we know that means is 1 dozen means 12. Well, the mole is the exact same thing, except it represents a much larger number than 12. So, how do we use the dozen? Well, for example, when buying eggs, 12 is just a convenient number to buy at one time. It makes pricing them easier. It makes the containers that they come in standardized easier, and all those sorts of things. So it's just a convenient number that becomes easier to work with than selling eggs as an individual egg. So if you imagine if you paid something like $2.40 for a dozen eggs, you'd be paying like 20 cents for each egg. But 20 cents for an egg it's just harder to work with. Dozen is a nice grouping for them to come in. Same idea with donuts. If you're buying donuts for a group of people, then if it's a very large group of people, you might be able to say, like, I want 5 or 6 dozen donuts, and it's just more convenient or easier to use than saying you want 60 or 72 donuts or whatever, because 60 or 72 is just a lot to think about. So we put them in this convenient package size, and that helps make it simpler. So how do we use the mole? Well, we use it in the same way. The number of particles in a typical substance is enormous. It's so enormous that it becomes hard to work with. We might say, we had 6.02 times 10 to the 23 water molecules, but that is so big it becomes meaningless. If we say we had 1 mole of water molecules, it's just a more convenient grouping to think of. Basically what it does from a mathematical perspective is it hides the difficult number of particles that we're really dealing with. Like if we had some crazy number of particles, right, like just some, I don't even know how you would pronounce this number. That might be like 10 moles. And you can see this number is usable, this number, it's not usable. So really all we're trying to do is we're trying to handle the fact that there are so many atoms that make up any substance that we ever look at. And so we're trying to package them into groups that make them more convenient, just like we packaged eggs into the carton of the dozen. Why did they choose 6.02 times 10 to the 23? Isn't that number a little bit silly? And that number is a lot easier to understand if you realize something important about the mole. They started using moles in chemistry before they knew how big the atom was. So they started using moles to compare how much hydrogen, for example, would react with oxygen gas to produce water. So something that they would have said is that 2 moles of hydrogen gas will react with 1 mole of oxygen gas and produce 2 moles of water. They started doing all of that, and they set, what they did is they set 1 mole of carbon 12 to weigh 12 grams long before they had any idea what the mass of a carbon-12 atom really was. That was a big mystery. So what that means then is later, when they figured out this number, they got this number which was like something times 10 to the negative 26. And then they worked backwards to figure out how much is in 12 grams. That led them to the number of the mole. So they never chose 6.02 times 10 to the 23. I suppose if they were going to choose something, they would have chose something that was round and easier to work with. But what they did instead is they just started working with it without knowing how big their package was. They only knew their packages relative to each other. And they used something reasonable, carbon-12 being 12 grams. That made hydrogen, which is the smallest thing, approximately 1 gram. So that's really why they would do that, right? Otherwise, hydrogen would end up being some decimal place. So they wanted 1 mole of hydrogen to be about 1 gram. So they made, but this is the standard. This is what they actually set the whole system up using. Then, once they set this, later when they found the mass of a carbon-12 atom, that set how many particles were in 12 grams of carbon. So it all developed backwards, and this number, which is called Avogadro's number, or sometimes we abbreviate that to NA, wasn't a choice that scientists made, but more a result. This is the choice they made. They said 12 grams of carbon is what we're going to call 1 mole. That was the choice they made. That set it up so 1 mole of hydrogen would be 1 gram. And then once they had done that, later they went back and said, so how many particles does that work out to be? And they got 6.02 times 10 to the 23. All right, so using Avogadro's number, how can we figure out how many atoms we actually have? Well, here, just imagine this. What if I told you have 5 dozen donuts? How would you figure out how many donuts you have? What you would do is you would take your number of dozen, 5, times the set number that a dozen represents, 12. And that would tell you your number of donuts. In this case, 60 donuts and 5 dozen. We can apply that same basic reasoning to figure out the number of particles in a substance. The number of particles is going to be equal to the number of moles, which we represent with little n. I don't write n for moles, but that's just what they do, times Avogadro's number, as in the number of particles in an individual mole. See, 5 times 12 gave us 5 dozen. Here we would have some number of moles times the number in each mole. Let's say I had 5 moles, then I would times that by 6.02 times 10 to the 23. That's how many particles in each mole. And I would get 3.01 times 10 to the 24 particles. Now, some chemists wouldn't look at it in a formula form like this. Oh, by the way, and we can rearrange this formula. The standard way of writing is that the number of moles is equal to the number of particles divided by Avogadro's number. Some chemists don't like to use this equation here. They like to use something called the factor reduction method. In this method, we're going to treat all of these numerical problems as if we're changing units, or as if we're converting from one unit to another unit. In this case, if we had 5 moles of something, then what we would have to do is we'd have to know how many particles per mole do we have if we wanted to convert this thing into particles. Here we can see moles on the top and moles on the bottom cancel out, and we're just left with particles. And for every 1 mole, we have 6.02 times 10 to the 23 particles. So this is a calculation that, or this is an approach that's much more similar to what we would do when we're converting units. We cancel out the old unit and introduce the new unit, and really what we recognize is we're just moving from the unit of moles to the unit of particles. Either way, you can see this is still 5 times 6, and so we get the same answer that we had before, 3.01 times 10 to the 24. So these are obviously just, right, it was 5 times 6 or 5 times 6. They're just two ways of thinking about the same thing. We can think about them the way that we did when we did donuts and come up with an equation and use that equation. Or we can think of it as moles as just a unit for the number of particles, and then we can convert to the number of particles, just like we might do, say, if we had 5 kilometers and we wanted to convert into meters. So that's the mole. That's our very first introduction to it. We're going to spend a lot of time talking about it over the next few videos, but I thought that would give us a good starting point.